This sound file contains the spoken version of a Wikipedia article on colonization of Mars recorded by user AJ Schull. The material recorded is current as of the 8th of April 2021. Colonization of Mars from Wikipedia, the free encyclopedia, at en.wikipedia.org. The hypothetical colonization of Mars has received interest from public space agencies and private corporations, and has received extensive treatment in science fiction writing, film, and art. Organizations have proposed plans for a human mission to Mars, the first step towards any colonization effort, but no person has set foot on the planet. However, landers and rovers have successfully explored the planetary surface and delivered information about conditions on the ground. Virtual visits to Mars using haptic technologies have been proposed and may precede humans visiting the planet. Reasons for colonizing Mars include curiosity, the potential for humans to provide more in-depth observational research than unmanned rovers, economic interest in its resources, and the possibility that the settlement of other planets could decrease the likelihood of human extinction. Difficulties and hazards include radiation exposure during a trip to Mars and on its surface, toxic soil, low gravity, the isolation that accompanies Mars's distance from Earth, a lack of water, and cold temperatures. The most recent commitments to researching permanent settlement include those by public space agencies NASA, ESA, Roscosmos, ISRO, and the CNSA, and private organizations SpaceX, Lockheed Martin, and Boeing. This section is accompanied by two images. The first image has the caption, "An artist's conception of a human Mars habitat with a 3D printed dome made of water ice, an airlock, and a pressurized Mars rover." The second image has the caption, "An artist's conception of a human Mars base, with a cutaway revealing an interior horticultural area." This article contains 18 sections. These sections are Section 1, Mission Concepts and Timelines, Section 2, Relative Similarity to Earth, Section 3, Differences between Earth and Mars, Section 4, Conditions for Human Habitation, Section 5, Transportation, Section 6, Equipment Needed for Colonization, Section 7, Robotic Precursors, Section 8, Economics, Section 9, Possible Locations for Settlements, Section 10, Planetary Protection, Section 11, Ethical, Political, and Legal Challenges, Section 12, Advocacy, Section 13, In Fiction, Section 14, Interactive Mars Map, Section 15, See Also, Section 16, References, Section 17, Further Reading, Section 18, External Links. Section 1, Mission Concepts and Timelines. Since the 20th century, there have been several proposed human missions to Mars, both by government agencies and private companies. All of the human mission concepts as currently conceived by national governmental space programs would not be direct precursors to colonization. Programs such as those being tentatively planned by NASA, Roscosmos, and ESA are intended solely as exploration missions, with the establishment of a permanent base possible, but not yet the main goal. Colonization requires the establishment of permanent habitats that have the potential for self-expansion and self-sustenance. Two early proposals for building habitats on Mars are the Mars Direct and the Semi-Direct concepts, advocated by Robert Zubrin, an advocate of the colonization of Mars. SpaceX has proposed the development of Mars transportation infrastructure in order to facilitate the eventual colonization of Mars. The mission architecture includes fully reusable launch vehicles, human-rated spacecraft, on-orbit propellant tanks, rapid turnaround launch/landing mounts, and local production of rocket fuel on Mars via in situ resource utilization, ISRU. SpaceX's aspirational goal is to land the first humans on Mars by 2024. This section is accompanied by one image. The image has a caption of "Artist's rendition of various components of a human Mars surface mission." Section 2, Relative Similarity to Earth. Earth is similar to Venus in bulk composition, size, and surface gravity, but Mars's similarities to Earth are more compelling when considering colonization. These include The Martian day, or sol, is very close in duration to Earth's. A solar day on Mars is 24 hours, 39 minutes, and 35.244 seconds. Mars has a surface that is 28.4% of Earth's, which is only slightly less than the amount of dry land on Earth, which is 29.2% of Earth's surface. Mars is half the radius of Earth and only 1/10 the mass. This means that it has a smaller volume, around 15%, and lower average density than Earth. Mars has an axial tilt of 25.19 degrees, similar to Earth's 23.44 degrees. As a result, Mars has seasons much like Earth, though on average they last nearly twice as long, because the Martian year is about 1.88 Earth years. Observations by NASA's Mars Reconnaissance Orbiter, ESA's Mars Express, and NASA's Phoenix lander confirm the presence of water ice on Mars. Section 3. Differences between Earth and Mars. Subsection 3.1. Gravity and magnetosphere. The surface gravity of Mars is just 38% that of Earth. Although microgravity is known to cause health problems such as muscle loss and bone demineralization, it is not known if Martian gravity would have a similar effect. The Mars Gravity Biosatellite was a proposed project designed to learn more about what effects Mars's lower surface gravity would have on humans, but it was cancelled due to a lack of funding. Due to the lack of a magnetosphere, solar particle events and cosmic rays can easily reach the Martian surface. This subsection is accompanied by a table, entitled Atmospheric Pressure Comparison. First column, location. Second column, pressure. First column, first row. Olympus Mons Summit. Second column, first row, 0.03 kPa, or 0.0044 psi. First column, second row, Mars average. Second column, second row, 0.6 kPa, 0.087 psi. First column, third row, Hellas Planitia bottom. Second column, third row, 1.16 kPa, 0.168 psi. First column, fourth row, Armstrong limit. Second column, fourth row, 6.25 kPa, 0.906 psi. First column, fifth row, Mount Everest summit. Second column, fifth row, 33.7 kPa, 4.89 psi. First column, sixth row, Earth sea level. Second column, sixth row, 101.3 kPa, 14.69 psi. Subsection 3.2, the atmosphere. Atmospheric pressures on Mars is far below the Armstrong limit, at which people can survive without pressure suits. Since terraforming cannot be expected as a near-term solution, habitable structures on Mars would need to be constructed with pressure vessels similar to spacecraft, capable of containing a pressure between 30 and 100 kPa. The atmosphere is also toxic, as most of it consists of carbon dioxide, 95% carbon dioxide, 3% nitrogen, 1.6% argon, and traces totaling less than 0.4% of other gases, including oxygen. This thin atmosphere does not filter out ultraviolet sunlight, which causes instability in the molecular bonds between atoms. For example, ammonia, NH3, is not stable in the Martian atmosphere and breaks down after a few hours. Also, due to the thinness of the atmosphere, the temperature difference between day and night is much larger than on Earth, typically around 70 degrees Celsius, 125 degrees Fahrenheit. However, the day/night temperature variation is much lower during dust storms, when very little light gets through to the surface even during the day, and instead warms the middle atmosphere. Subsection 3.3. Water and climate. Water on Mars is scarce, with rovers Spirit and Opportunity finding less than there is in Earth's driest desert. The climate is much colder than Earth, with mean surface temperatures between 186 and 268 Kelvin, -87 and -5 degrees Celsius, -125 and 23 degrees Fahrenheit, depending on the season and latitude. The lowest temperature ever recorded on Earth was 184 Kelvin, -89.2 degrees Celsius, -128.6 degrees Fahrenheit in Antarctica. Because Mars is about 52% farther from the Sun, the amount of solar energy entering its upper atmosphere per unit area, the solar constant, is only around 43.3% of what reaches the Earth's upper atmosphere. However, due to the much thinner atmosphere, a higher fraction of the solar energy reaches the surface. The maximum solar irradiance on Mars is about 590 W per m squared compared to about 1,000 W per m squared at the Earth's surface. Optimal conditions on the Martian equator can be compared to those on Devon Island in the Canadian Arctic in June. Global dust storms are common throughout the year and can cover the entire planet for weeks, blocking sunlight from reaching the surface. This has been observed to cause temperature drops of 4 degrees Celsius, 7 degrees Fahrenheit, for several months after the storm. In contrast, the only comparable events on Earth are infrequent large volcanic eruptions, such as Krakatoa, which threw large amounts of ash into the atmosphere in 1883, causing a global temperature drop of around 1 degrees Celsius, 2 degrees Fahrenheit. Perhaps more importantly, these storms affect electricity production from solar panels for long periods, as well interfering with communications with Earth. Mars has no rain and virtually no clouds, so although cold, it is permanently sunny, apart from during dust storms. This means solar panels can always operate at maximum efficiency on dust-free days, and Mars's orbit is more eccentric than Earth's, increasing temperature and solar constant variations over the course of a Martian year. Subsection 3.4 Soil. The Martian soil is toxic due to relatively high concentrations of chlorine and associated compounds which are hazardous to all known forms of life. Subsection 3.5 Survivability. Although there are some extremophile organisms that survive in hostile conditions on Earth, including simulations that approximate Mars, plants and animals generally cannot survive the ambient conditions present on the surface of Mars. Section 4 Conditions for human habitation. Conditions on the surface of Mars are closer to the conditions on Earth in terms of temperature and sunlight than on any other planet or moon except for the cloud tops of Venus. However, the surface is not hospitable to humans or most known life forms due to the radiation, greatly reduced air pressure, and an atmosphere with only 0.16% oxygen. In 2012, it was reported that some lichen and cyanobacteria survived and showed remarkable adaptation capacity for photosynthesis after 34 days in simulated Martian conditions in the Mars Simulation Laboratory, MSL, maintained by the German Aerospace Center, DLR. Some scientists think that cyanobacteria could play a role in the development of self-sustainable crewed outposts on Mars. They propose that cyanobacteria could be used directly for various applications, including the production of food, fuel, and oxygen, but also indirectly, products from their culture could support the growth of other organisms, opening the way to a wide range of life support biological processes based on Martian resources. Humans have explored parts of Earth that match some conditions on Mars. Based on NASA rover data, temperatures on Mars at low latitudes are similar to those in Antarctica. The atmospheric pressure at the highest altitudes reached by piloted balloon ascents, 35 kilometers, 114,000 feet in 1962, 38 kilometers in 2012, is similar to that on the surface of Mars. However, these pilots were not exposed to the extremely low pressure as it would have killed them, but seated in a pressurized capsule. Human survival on Mars would require living in artificial Mars habitats with complex life support systems. One key aspect of this would be water processing systems. Being made mainly of water, a human being would die in a matter of days without it. Even a 5 to 8% decrease in total body water causes fatigue and dizziness, and a 10% decrease physical and mental impairment. See dehydration. A person in the UK uses 70 to 140 liters of water per day on average. Through experience and training, astronauts in the ISS have shown it is possible to use far less, and around 70% of what is used can be recycled using the ISS water recovery systems. Half of all water is used during showers. Similar systems would be necessary on Mars, but would need to be much more efficient since regular robotic deliveries of water to Mars would be prohibitively expensive. The ISS is supplied with water 4 times per year. Potential access to in-situ water, frozen or otherwise via drilling, has been investigated by NASA. This section is accompanied by 2 images. The first image has the caption, "An expedition-style crewed mission would operate on the surface but for limited amounts of time." The second image has a caption, "Dust is one concern for Mars missions." Subsection 4.1 Effects on human health. Mars presents a hostile environment for human habitation. Different technologies have been developed to assist long-term space exploration and may be adapted for habitation on Mars. The existing record for the longest consecutive spaceflight is 438 days by cosmonaut Valery Polyakov, and the most accrued time in space is 878 days by Gennady Padelka. The longest time spent outside the protection of the Earth's Van Allen radiation belt is about 12 days for the Apollo 17 moon landing. This is minor in comparison to the 1,100-day journey planned by NASA as soon as the year 2028. Scientists have also hypothesized that many different biological functions can be negatively affected by the environment of Mars's colonies. Due to higher levels of radiation, there are a multitude of physical side effects that must be mitigated. In addition, Mars's soil contains high levels of toxins, which are hazardous to human health. Subsection 4.1.1 Physical Effects. The difference in gravity would negatively affect human health by weakening bones and muscles. There is also a risk of osteoporosis and cardiovascular problems. Current rotations of the International Space Station put astronauts in zero gravity for 6 months, a comparable length of time to a one-way trip to Mars. This gives researchers the ability to better understand the physical state that astronauts going to Mars would arrive in. Once on Mars, surface gravity is only 38% of that on Earth. Microgravity affects the cardiovascular, musculoskeletal, and neurovestibular central nervous systems. The cardiovascular effects are complex. On Earth, blood within the system stays 70% below the heart, and in microgravity, this is not the case due to nothing pulling the blood down. This can have several negative effects. Once entering into microgravity, the blood pressure in the lower body and legs is significantly reduced. This causes legs to become weak through the loss of muscle and bone mass. Astronauts show signs of a puffy face and chicken leg syndrome. After the first day of re-entry back to Earth, blood samples showed a 70% loss of blood plasma, which contributed to a decline of erythropoietin secretion. On the skeletal system, which is important to support our body's posture, long space flights and exposure to microgravity cause demineralization and atrophy of muscles. During reacclimation, astronauts were observed to have a myriad of symptoms including cold sweats, nausea, vomiting, and motion sickness. Returning astronauts also felt disoriented. Journeys to and from Mars being 6 months is the average time spent at the ISS. Once on Mars with its lesser surface gravity, 38% of Earth's, these health effects would be a serious concern. Upon return to Earth, recovery from bone loss and atrophy is a long process, and the effects of microgravity may never fully reverse. Subsection 4.1.2 Radiation. Mars has a weaker global magnetosphere than Earth does, as it has lost its inner dynamo, which significantly weakened the magnetosphere, the cause of so much radiation reaching the surface, despite its far distance from the Sun compared to Earth. Combined with a thin atmosphere, this permits a significant amount of ionizing radiation to reach the Martian surface. There are two main types of radiation risks to traveling outside the protection of Earth's atmosphere and magnetosphere: galactic cosmic rays, GCR, and solar energetic particles, SEP. Earth's magnetosphere protects from charged particles from the Sun, and the atmosphere protects against uncharged and highly energetic GCRs. There are ways to mitigate against solar radiation, but without much of an atmosphere, the only solution to the GCR flux is heavy shielding amounting to roughly 15 centimeters of steel, 1 meter of rock, or 3 meters of water, limiting human colonists to living underground most of the time. The Mars Odyssey spacecraft carries an instrument, the Mars Radiation Environment Experiment, MARIE, to measure the radiation. MARIE found that radiation levels in orbit above Mars are 2.5 times higher than at the International Space Station. The average daily dose is about 222 micro-GY, 22 MRAD, equivalent to 0.08 GY per year. A 3-year exposure to such levels would exceed the safety limits currently adopted by NASA, and the risks of developing cancer due to radiation exposure after a Mars mission could be 2 times greater than what scientists previously thought. Occasional solar proton events, SPEs, provide much higher doses, as observed in September 2017, when NASA reported radiation levels on the surface of Mars were temporarily doubled and were associated with an aurora 25 times brighter than any observed earlier due to a massive and unexpected solar storm. Building living quarters underground, possibly in Martian lava tubes, would significantly lower the colonists' exposure to radiation. Much remains to be learned about solar radiation. In 2003, NASA's Lyndon B. Johnson Space Center opened a facility, the NASA Space Radiation Laboratory at Brookhaven National Laboratory, that employs particle accelerators to simulate space radiation. The facility studies its effects on living organisms, as well as experimenting with shielding techniques. Initially, there was some evidence that this kind of low-level chronic radiation is not quite as dangerous as once thought, and that radiation hormesis occurs. However, results from a 2006 study indicated that protons from cosmic radiation may cause twice as much serious damage to DNA as previously estimated, exposing astronauts to greater risk of cancer and other diseases. As a result of the higher radiation in the Martian environment, the summary report of the Review of U.S. Human Spaceflight Plans Committee released in 2009 reported that, quote, Mars is not an easy place to visit with existing technology and without a substantial investment of resources, end quote. NASA is exploring a variety of alternative techniques and technologies such as deflector shields of plasma to protect astronauts and spacecraft from radiation. This section is accompanied by an image, which is the caption, Comparison of radiation doses includes the amount detected on the trip from Earth to Mars by the RAD on the MSL. 2011 to 2013. Subsection 4.1.3, Psychological Effects. Due to the communication delays, new protocols need to be developed in order to assess crew members' psychological health. Researchers have developed a Martian simulation called HISEAS, Hawaii Space Exploration, Analog, and Simulation, that places scientists in a simulated Martian laboratory to study the psychological effects of isolation, repetitive tasks, and living in close quarters with other scientists for up to a year at a time. Computer programs are being developed to assist crews with personal and interpersonal issues in absence of direct communication with professionals on Earth. Current suggestions for Mars exploration and colonization are to select individuals who have passed psychological screenings. Psychosocial sessions for the return home are also suggested in order to reorient people to society. Subsection 4.2, Terraforming. Various works of fiction put forward the idea of terraforming Mars to allow a wide variety of life forms, including humans, to survive unaided on Mars' surface. Some ideas of possible technologies that may be able to contribute to the terraforming of Mars have been conjectured, but none would be able to bring the entire planet into the Earth-like habitat pictured in science fiction. This section is accompanied by an image. The image has the caption, Artist's conception of the process of terraforming Mars as discussed in some works of science fiction. Section 5, Transportation. Subsection 5.1, Interplanetary Spaceflight. Mars requires less energy per unit mass, delta V, to reach from Earth than any planet except Venus. Using a Hohmann transfer orbit, a trip to Mars requires approximately 9 months in space. Modified transfer trajectories that cut the travel time down to 4 to 7 months in space are possible with incrementally higher amounts of energy and fuel compared to a Hohmann transfer orbit, which are in standard use for robotic Mars missions. Shortening the travel time below about 6 months requires higher delta V and an increasing amount of fuel, which is difficult with chemical rockets. It could be feasible with advanced spacecraft propulsion technologies, some of which have already been tested to varying levels, such as variable specific impulse magnetoplasma rocket and nuclear rockets. In the former case, a trip time of 40 days could be attainable, and in the latter, a trip time down to about 2 weeks. In 2016, a University of California, Santa Barbara scientist said they could further reduce travel time for a small robotic probe to Mars down to, quote, as little as 72 hours, end quote, with the use of a laser-propelled sail, directed photonic propulsion system instead of the fuel-based rocket propulsion system. During the journey, the astronauts would be subject to radiation, which would require a means to protect them. Cosmic radiation and solar wind cause DNA damage, which increases the risk of cancer significantly. The effect of long-term travel in interplanetary space is unknown, but scientists estimate an added risk of between 1% and 9%. One estimate is 3.4% for males to die of cancer because of the radiation during the journey to Mars and back to Earth. For females, the probability is higher due to generally larger glandular tissues. This section is accompanied by 2 images. The first image is the caption Mars, Viking 1, 1980. The second image is the caption Rendezvous, an interplanetary stage and lander stage coming together over Mars. Subsection 5.2, Landing on Mars. Mars has a surface gravity 0.38 times that of Earth, and the density of its atmosphere is about 0.6% of that on Earth. The relatively strong gravity and the presence of aerodynamic effects make it difficult to land heavy, crewed spacecraft with thrusters only, as was done with the Apollo moon landings, yet the atmosphere is too thin for aerodynamic effects to be much of help in aerobraking and landing a large vehicle. Landing piloted missions on Mars would require braking and landing systems different from anything used to land crewed spacecraft on the moon or robotic missions on Mars. If one assumes carbon nanotube construction material will be available with a strength of 130 GPa, 19 million psi, then a space elevator could be built to land people and material on Mars. A space elevator on Phobos, a Martian moon, has also been proposed. This section is accompanied by one image. The image's caption is Painting of a Landing on Mars, 1986. Section 6. Equipment needed for colonization. Colonization of Mars would require a wide variety of equipment, both equipment to directly provide services to humans and production equipment used to produce food, propellant, water, energy, and breathable oxygen, in order to support human colonization efforts. Required equipment would include basic utilities, oxygen, power, local communications, waste disposal, sanitation and water recycling, habitats, storage facilities, shop workspaces, airlock for pressure and dust management, resource extraction equipment, initially for water and oxygen, later for wider cross-section of materials, building materials, etc., equipment for energy production and energy storage, some solar and perhaps nuclear as well, food production spaces and equipment, propellant production equipment generally thought to be hydrogen and methane through the Sabatier reaction for fuel with oxygen oxidizer for chemical rocket engines, fuels or other energy source for use with surface transportation, carbon monoxide / oxygen CO / O2 engines have been suggested for early surface transportation use, as both carbon monoxide and oxygen can be straightforwardly produced by zirconium dioxide electrolysis from the Martian atmosphere without requiring use of any of the Martian water resources to obtain hydrogen. Off-planet communication equipment, equipment for moving over the surface, Mars suit crewed rovers, and possibly even Mars aircraft. This section contains one image with the caption, Mars greenhouses feature in many colonization designs, especially for food production and other purposes. Subsection 6.1. Basic utilities. In order to function at all, the colony would need basic utilities to support human civilization. These would need to be designed to handle the harsh Martian environment and would either have to be serviceable whilst wearing an EVA suit or housed inside a human habitable environment. For example, if electricity generation systems rely on solar power, large energy storage facilities will also be needed to cover the periods when dust storms block out the sun, and automatic dust removal systems may be needed to avoid human exposure to conditions on the surface. If the colony is to scale beyond a few people, systems will also need to maximize use of local resources to reduce the need for resupply from Earth. For example, by recycling water and oxygen and being adapted to be able to use any water found on Mars, whatever form it is in. This section is accompanied by one image. The image's caption is, Various technologies and devices for Mars are shown in the illustration of a Mars's base. Subsection 6.2. Communication with Earth. Communications with Earth are relatively straightforward during the half-sol when Earth is above the Martian horizon. NASA and ESA included communications relay equipment in several of Mars' orbiters, so Mars already has communications satellites. While these will eventually wear out, additional orbiters with communications relay capability are likely to be launched before any colonization expeditions are mounted. The one-way communication delay due to the speed of light ranges from about 3 minutes at closest approach, approximated by perihelion of Mars minus aphelion of Earth, 22 minutes at the largest possible superior conjunction, approximated by aphelion of Mars plus aphelion of Earth. Real-time communications, such as telephone conversations or internet relay chat between Earth and Mars, would be highly impractical due to the long time lags involved. NASA has found that direct communication can be blocked for about 2 weeks every synodic period, around the time of superior conjunction when the Sun is directly between Mars and Earth. Although the actual duration of the communication blockout varies from mission to mission depending on various factors, such as the amount of link margin designed into the communication system and the minimum data rate that is acceptable from a mission standpoint, in reality, most missions at Mars have had communication blackout periods of the order of a month. A satellite at the L4 or L5 Earth-Sun Lagrangian point could serve as a relay during this period to solve the problem. Even a constellation of communication satellites would be a minor expense in the context of a full colonization program. However, the size and power of the equipment needed for these distances make the L4 and L5 locations unrealistic for relay stations, and the inherent stability of these regions, although beneficial in terms of station keeping, also attracts dust and asteroids, which could pose a risk. Despite that concern, the stereo probes passed through the L4 and L5 regions without damage in late 2009. Recent work by the University of Strathclyde's Advanced Space Concept Laboratory, in collaboration with the European Space Agency, has suggested an alternative relay architecture based on highly non-Keplerian orbits. These are a special kind of orbit produced when continuous low-thrust propulsion, such as that produced from an ion engine or solar sail, modifies the natural trajectory of a spacecraft. Such an orbit would enable continuous communications during solar conjuncture by allowing a relay spacecraft to hover above Mars, out of the orbital plane of the two planets. Such a relay avoids the problems of satellites stationed either L4 or L5 by being significantly closer to the surface of Mars while still maintaining continuous communication between the two planets. Section 7. Robotic Precursors. The path to a human colony could be prepared by robotic systems, such as the Mars exploration rovers Spirit, Opportunity, Curiosity, and Perseverance. These systems could help locate resources such as groundwater or ice that would help a colony grow and thrive. The lifetimes of these systems would be years and even decades, and as recent developments in commercial spaceflight have shown, it may be that these systems will involve private as well as government ownership. These robotic systems also have a reduced cost compared with early crewed operations and have less political risk. Wired systems may lay the groundwork for early crewed landings and bases by producing various consumables, including fuel, oxidizers, water, and construction materials. Establishing power, communications, shelter, heating, and manufacturing basics can begin with robotic systems, if only as a prelude to crewed operations. Mars Surveyor 2001 lander MIP, Mars ISPP precursor, was to demonstrate manufacture of oxygen from the atmosphere of Mars, and test solar cell technologies and methods of mitigating the effects of Martian dust on the power systems. Before any people are transported to Mars on the notional 2020s Mars transportation infrastructure envisioned by SpaceX, a number of robotic cargo missions would be undertaken first in order to transport the requisite equipment, habitats, and supplies. Equipment that would be necessary would include machines to produce fertilizer, methane, and oxygen from Mars's atmospheric nitrogen and carbon dioxide and the planet's subsurface water ice, as well as construction materials to build transparent domes for initial agricultural areas. This section is accompanied by one image. The image's caption is Astronauts Approaching Viking 2 Lander Probe. Section 8. Economics. As with early colonies in the New World, economics would be a crucial aspect to a colony's success. The reduced gravity well of Mars and its position in the solar system may facilitate Mars-Earth trade, and may provide an economic rationale for continued settlement of the planet. Given its size and resources, this might eventually be a place to grow food and produce equipment to mine the asteroid belt. Some early Mars colonies might specialize in developing local resources for Martian consumption, such as water and/or ice. Local resources can also be used in infrastructure construction. One source of Martian ore currently known to be available is metallic iron in the form of nickel-iron meteorites. Iron in this form is more easily extracted than from the iron oxides that cover the planet. Another main inter-Martian trade good during early colonization could be manure. Assuming that life doesn't exist on Mars, the soil is going to be very poor for growing plants, so manure and other fertilizers will be highly valued in any Martian civilization until the planet changes enough to chemically support growing vegetation on its own. Solar power is a candidate for power for a Martian colony. Solar insolation, the amount of solar radiation that reaches Mars, is about 42% of that of Earth. Since Mars is about 52% farther from the Sun, and insolation falls off as the square of distance. But the thin atmosphere would allow almost all that energy to reach the surface as compared to Earth, where the atmosphere absorbs roughly a quarter of the solar radiation. Sunlight on the surface of Mars would be much like a moderately cloudy day on Earth. This section is accompanied with an image. The image's caption is Iron-Nickel Meteorite Found on Mars' Surface, Heat Shield Rock. Subsection 8.1. Economic Drivers. Space colonization on Mars can roughly be said to be possible when the necessary methods of space colonization become cheap enough, such as space access by cheaper launch systems, to meet the cumulative funds that have been gathered for the purpose. Although there are no immediate prospects for the large amounts of money required for any space colonization to be available given traditional launch costs, there is some prospect of a radical reduction to launch costs in the 2020s, which would consequently lessen the cost of any efforts in that direction. With a published price of US dollars 62 million per launch of up to 22,800 kilograms, 50,300 pounds, payload to low Earth orbit, or 4,020 kilograms, 8,860 pounds to Mars, SpaceX Falcon 9 rockets are already the, quote, cheapest in the industry, end quote. SpaceX reusable plans include Falcon Heavy and future methane-based launch vehicles, including the Starship. If SpaceX is successful in developing the reusable technology, it would be expected to, quote, have a major impact on the cost of access to space, end quote, and change the increasingly competitive market in space launch services. Alternative funding approaches might include the creation of inducement prizes. For example, the 2004 President's Commission on Implementation of United States Space Exploration Policy suggested that an inducement prize contest should be established, perhaps by government, for the achievement of space colonization. One example provided was offering a prize to the first organization to place humans on the moon and sustain them for a fixed period before they return to Earth. Section 9. Possible locations for settlements. Subsection 9.1. Equatorial regions. Mars Odyssey found what appeared to be natural caves near the volcano Arsia Mons. It has been speculated that settlers could benefit from the shelter that these or similar structures could provide from radiation and micrometeoroids. Geothermal energy is also suspected in the equatorial regions. Subsection 9.2. Lava tubes. Several possible Martian lava tube skylights have been located on the flanks of Arsia Mons. Earth-based examples indicate that some should have lengthy passages offering complete protection from radiation and be relatively easy to seal using on-site materials, especially in small subsections. This section is accompanied by one image. The image's caption is cropped version of a high-rise image of a lava tube skylight entrance on the Martian volcano Pavonis Mons. Subsection 9.3. Hellas Planitia. Hellas Planitia is the lowest lying plain below the Martian geodetic datum. The air pressure is relatively higher in this place when compared to the rest of Mars. Section 10. Planetary protection. Robotic spacecraft to Mars are required to be sterilized to have at most 300,000 spores on the exterior of the craft, and more thoroughly sterilized if they contact, quote, special regions, end quote, containing water. Otherwise, there is a risk of contaminating not only the life detection experiments, but possibly the planet itself. It is impossible to sterilize human missions to this level, as humans are host to typically 100 trillion microorganisms of thousands of species of the human microbiome, and these cannot be removed while preserving the life of the human. Containment seems the only option, but it is a major challenge in the event of a hard landing, i.e. crash. There have been several planetary workshops on this issue, but with no final guidelines for a way forward yet. Human explorers would also be vulnerable to back contamination to Earth if they become carriers of microorganisms should Mars have life. Section 11. Ethical, political, and legal challenges. It is unforeseen how the first human landing on Mars will change the current policies regarding the exploration of space and occupancy of celestial bodies. In the 1967 United Nations Outer Space Treaty, it was determined that no country may take claim to space or its inhabitants. Since the planet Mars offers a challenging environment and dangerous obstacles for humans to overcome, the laws and culture on the planet will most likely be very different from those on Earth. With Elon Musk announcing his plans to travel to Mars, it is uncertain how the dynamic of a private company possibly being the first to put a human on Mars will play out on a national and global scale. NASA had to deal with several cuts in funding. During the presidency of Barack Obama, the objective for NASA to reach Mars was pushed into the background. In 2017, President Donald Trump promised to return humans to the moon and eventually Mars, effectively taking action by increasing NASA budget with $1.1 billion US dollars, and mostly focus on the development of the new space launch system. Subsection 11.1 Colonialism. Space colonization in general has been discussed as continuation of imperialism and colonialism, especially regarding Mars colonial decision-making and reasons for colonial labor and land exploitation have been questioned with post-colonial critique. Seeing the need for inclusive and democratic participation in the implementation of any space and Mars exploration, infrastructure, or colonization, many have called for dramatic sociological reforms and guarantees to prevent racism, sexism, and other forms of prejudice and bigotry. The narrative of space exploration as the, quote, new frontier, end quote, has been criticized as unreflected continuation of settler colonialism and manifest destiny, continuing the narrative of colonial exploration as fundamental to the assumed human nature. The predominant perspective of territorial colonization in space has been called surfacism, especially comparing advocacy for colonization of Mars opposed to Venus. Subsection 11.2 Dangers to pregnancy. One possible ethical challenge that space travelers might face is that of pregnancy during the trip. According to NASA's policies, it is forbidden for members of the crew to engage in sex in space. NASA wants its crew members to treat each other like coworkers would in a professional environment. A pregnant member on a spacecraft is dangerous to all those on board. The pregnant woman and child would need additional nutrition from the rations aboard, as well as special treatment and care. The pregnancy would impede on the pregnant crew members' duties and abilities. It is still not fully known how the environment in a spacecraft would affect the development of a child aboard. It is known, however, that an unborn child in space would be more susceptible to solar radiation, which would likely have a negative effect on its cells and genetics. During a long trip to Mars, it is likely that members of the craft may engage in sex due to their stressful and isolated environment. This section is accompanied by one image. The image's caption is, "The logo and name of the Lunar Gateway references the St. Louis Gateway Arch, associating Mars with the American frontier." Section 12. Advocacy. Mars colonization is advocated by several non-governmental groups for a range of reasons and with varied proposals. One of the oldest groups is the Mars Society, who promote a NASA program to accomplish human exploration of Mars and have set up Mars analog research stations in Canada and the US. Mars to Stay advocates recycling emergency return vehicles into permanent settlements as soon as initial explorers determine permanent habitation is possible. Elon Musk founded SpaceX with the long-term goal of developing the technologies that will enable a self-sustaining human colony on Mars. In 2015, he stated, "I think we've got a decent shot of sending a person to Mars in 11 or 12 years, as in 2026 to 27. Richard Branson is, quote, "determined to be a part of starting a population on Mars. I think it is absolutely realistic. It will happen, I think, over the next 20 years. End quote. From 2012, quote, "We will take literally hundreds of thousands of people to space, and that will give us the financial resources to do even bigger things." In June 2013, Buzz Aldrin, American engineer and former astronaut, and the second person to walk on the moon, wrote an opinion published in the New York Times supporting a human mission to Mars and viewing the moon, quote, "not as a destination, but more a point of departure, one that places humankind on a trajectory to homestead Mars and become a two-planet species," end quote. In August 2015, Aldrin, in association with the Florida Institute of Technology, presented a, quote, "master plan," end quote, for NASA consideration for astronauts with a, quote, "tour of duty of 10 years," end quote, to colonize Mars before the year 2040. This section is accompanied by one image. The image's caption is, "Buzz Aldrin, the Apollo 11 astronaut and second person to set foot on the moon, has recommended human Mars missions." Section 13. In fiction. A few instances in fiction provide detailed descriptions of Mars colonization. They include Away, 2020, published by Netflix; Surviving Mars, 2018, developed by Haymont Games, published by Paradox Interactive; The Expanse, 2016 to 2021, airing originally on Sci-Fi, then Amazon Prime; Terra Genesis, 2016, developed by Edgeworks Entertainment, published by Tilting Point; The Space Between Us, 2016 film by Peter Chesham; Mars, 2016 by National Geographic; John Carter, 2012 by Mark Andrews. The Martian, 2011 by Andy Weir in the 2015 film directed by Ridley Scott. Mr. Nobody, 2009 by Jacob Van Drommel. Tom and Jerry Blast Off to Mars, 2005, animated science fiction comedy film by Warner Bros. Animation and Turner Entertainment. Aria, 2002 to 2008 by Kozu Amano. First Landing, 2002 by Robert Zubrin. Red Faction, 2001, developed by Volition, published by THQ. Mars Diaries, 2000 by Sigmund Brewer. Martian Gothic, Unification, 2000, developed by Creative Reality for Microsoft Windows and Coyote Developments for PlayStation, published by Talonsoft for Microsoft Windows and Take-Two Interactive for PlayStation. Mars Underground, 1997, by William K. Hartman. Climbing Olympus, 1994, by Kevin J. Anderson. The Martian, 1992, and Return to Mars, 1999, by Ben Bova. Total Recall, 1990, by Paul Verhoeven. Icehenge, 1985, The Mars Trilogy, Red Mars, Green Mars, Blue Mars, 1992 to 1996, and The Martians, 1999, by Kim Stanley Robinson. Man Plus, 1976, by Frederick Pohl. The Destruction of Fana, 1974, by Alexander Kazantsev. We Can Remember It For You Wholesale, 1966, by Philip K. Dick. The Sands of Mars, 1951, by Arthur C. Clarke. The Martian Chronicles, 1950, by Ray Bradbury. Section 14. Interactive Mars Map. This section consists of an interactive image map of the global topography of Mars. This sound file and all text in the article are licensed under Creative Commons Attribution-Share Alike 3.0 Unported License, available at creativecommons.org/licenses/by-SA/3.0.